First of all, we're given here a truss, pin supported at point B, roller supported at E, or in other words, a truss that is simply supported at B and at E, with all these forces acting on it. 4 kilonewtons at A, 6 kilonewtons at C, 3 kilonewtons at D, and a horizontal 2 kilonewton force at F. So our goal here is to find the tension in the cables. HC is a cable, also BG, GD, and CF. So when you talk about cables, this structural member can only support a tension force. So you can imagine it as a rope. So if you apply a tension on it, if you pull the rope, of course it will resist that force that you apply. But if you apply compression, on the other hand, you push on the ropes, it will just bend and will not resist that force. So cable can only support a tension force. Now to find the force in it, inside it, the force in H, C, BG, and all the cables present in our example, we will just have to expose that force, or in other words, cut that member, so we can analyze its equilibrium or analyze the structure. So if we cut that the rope along HG, the two cables, and BC, it will look like this, just like that. And this method here we're doing is what they call method of sections, because it's more like cutting the members into sections, just like this one. This is the portion on the left if we cut the truss here. Alright, now that the ropes is being exposed, we can now find the forces in it. But then due to number of unknowns here, it's like here, we know that the pin can only support vertical and horizontal reactions, and we have the number of unknowns BC, BG, this member right here, since it's being cut, so this must have a force as well, that BC, HG, and the two cables right here, they must have forces, right? And that unknowns amounts to 1, 2, 3, 4, 5, or 6 basically, these reactions. This. So there are 6 unknowns, and up to 3 equations is the only equations that we can have. So to lessen the unknowns here in this cut, we will consider the whole truss and find the forces that acts on it, ba? Or in other words, find first the external reactions, ba? The force in the pin, that's RBB, or the reaction of at B vertically, and its horizontal reactions, and also at E, ba? Or we could just directly solve for the reaction vertical at B. So we can find this one, and since this is already given, and here if we only consider vertical, we can just ignore these 3, ba? To take advantage of the vertical components of these horizontal forces, or the forces in the cable, ba? So now how we're going to find this force? This is RBV. Well, if we consider the whole truss, the free body diagram of that will be like this, ba? Since we are only concerned with RBV, or the reaction vertical at B, we can take moment at E, here. Sum all the moments at E is what? Must be equal to 0. Because if we say in equilibrium, all the forces must be balanced. Thus, the sum of all the forces translationally, or leftwards, upwards, or rightwards, must be 0. Also, rotationally, the moments, as they say, the torque must be balanced, or must be also equal to 0. There should not be a net force. Otherwise, our structure will move. It will no longer be balanced. Right? So that's it. Sum of the moments at E must be 0. So, since this is our goal, RBB, its moment arm is this. This is the perpendicular distance with respect to our force, and with respect to the point we're taking moment at. So that's at E. So RBV has a moment arm 3 plus 2 2.4s, or 2.4 plus 2.4. That's 2 2.4s. Right? And notice that this RBB rotates our truss. It rotates our truss clockwise direction, in the clockwise direction. So any force that could create also the same direction of this RBV must be added to RBV, right? Because counterclockwise or clockwise moments must be equal to counterclockwise moments for that to be in equilibrium. So what are these other forces? Turns out that it is the 2 kilonewton force, right? With its moment arm 3 meter. So plus 2 times 3. So these are all. Are there any other force that cause clockwise rotation? I guess there's no more, so that's these forces creates clockwise. Must be equal to forces that cause counterclockwise about point E. Point E. So this, and this. So 4 is about this entire distance, diba? This entire distance. So that's 4 times the moment arm 3 plus 3, or that's 2 threes plus 2 2.4s plus 6 this force times 2 2.4s plus 3 that force 3 times 2.4. All right, and since our only unknown here is RBV turns out to be 47 over 13 kilonewtons. All right, now that we have that 47 over 13 magnitude force here at RBV, we'll go back and put that right here, 47 over 13 kN. Or if we put that in decimal, that's about 9.38 kilonewtons. Ba? And this right here is exactly 4 kilonewtons. For example, if we have 5 kilonewtons upwards and we have only 3 kilonewtons downwards, then for that to be in equilibrium, we must add 2 kilonewtons downwards, right? That's the same idea we have here. We have an upward force 9.38 kilonewtons, downward force of 4 kilonewtons. Then the net force must be 4 point something upwards. Huh? The resultant is upwards. So in order for this to balance, so we can have 9.38 equals 9.38 forces upward and downward, then we must add something to 4. In order for that to become 9.38. And that's going to be 4.62. I guess 4.62. So here, if we change this as 9.38, here as well, change that at 9.38. This is 9.38, and here we only have 4. And this would be 4.62 for this to be in equilibrium. And which among these cables here, which among these carries a downward force? Turns out that this cable above is the only force that carries a downward force. Because otherwise, if we let this carry that 4.62 load, then it will add another 4.62 here. And it will become 13 point something. And here we only have 4. So it's wrong. It will not be in equilibrium. These diagonal forces, that is these cables right here, has horizontal and vertical components. Also, these red ones has horizontal and vertical components. And applying what we have just found out a while ago, that this 4.62 right here is the answer that could balance this 9.38 upward force right here. That force must be the vertical component of this cable. This cable can be named as tension HC. This one, HC. This cable, THC. So that is its vertical component. So just to see that, here's the blue. This one, 9.38 must be equal to this. Another blue, 4kn, or that's 4, plus this vertical component. That's 4.62, right? And this must be 0. The tension BG, this one, must be 0, because it's already balanced because of this THC vertical component. Now to find the force that's in THC actually, diba? It's only the vertical component. To find the force really that's acting on THC or or on HC, cable HC, you just have to consider the slope of that. This one here, it's 3 meters. This is 3 meters. And this also, its depth is also 3 meters. Right here, right there. Alright? So whenever we have, right there, just like that. Whenever we have 90-degree angle, whenever we have a triangle that's 90 degrees and has a sides the same, or what they call isosceles triangle, its angles must always equal to 45 degrees. Other than 90 degrees, the remaining angles must be 45 degrees if we have isosceles triangle. Applying that idea to what we have here, then if this is THC and this is 3 meters by 3 meters, then this angle right here must be 45 degrees. And we already know that this is the vertical component of THC. This is THC in terms of vertical. And we have a 45-degree angle. How do we find this THC? Well, if this is a triangle, a right angle triangle, then we can take advantage of our trigonometry. If we take cosine of 45 and say opposite over adjacent, opposite of that angle, this angle is THC vertical, right? So THC vertical all over the hypotenuse. This is the hypotenuse, this is the right angle, all over THC. We know that THCB is 4.62, again, due to these reasons. And since we know this information, we can now solve for the tension cable HC is carrying. And that turns out to be 4.62 all over cosine 45. THC must be about 6.53 kilonewtons. So this is how you find the tensions. This is 0. And I'll leave this part for you to try and solve for tension G, D, and tension D, CF. So that's it for this video, guys, and I hope you got something here. Thanks for watching. Peace out.